In this video, I intend to cover what we actually do with the inverse, and the reality is we use the inverse to solve matrix equations. So equations that have matrices in them, we can solve them. We use the inverse to do that. I really want to try and get out one of the most important things about this lesson during the first minute while you've really got a lot of focus, right? So my example here says, given matrices A and B below, solve for the matrix X if AX equals B. Okay, and then go on and solve the equation XA equals B. Right? So in both cases, we want to solve for the matrix X, which is here. Right? The important question is how do we do that? And the thought is, if I want to get X alone, I need to move A. I need to get that out of the problem. Right? And so the idea is we use the inverse to do that. If you want to cancel out an A, we need to apply the inverse. We need to multiply by the inverse. And when I said I was going to get to the most important part, here it is right here. The order in which you multiply matrices matters. So, if you put A inverse on the left side of AX, then you need to multiply the other side by the inverse on the left side of B. And the reason I mention that is that, in some sense, we've gotten really lazy in a lot of our math. If you had to solve this equation, what most people do is they write 1/7 on both sides. I mean, heck, some people will just take 7x equals 14 and do like this, which is really mathematically inaccurate. But the idea is, you just multiply this one on the left, but this one on the right. We're allowed to do that with normal multiplication because the order that you multiply things with normal multiplication doesn't matter. But with matrices, it does matter. It matters whether you put that thing on the left side or on the right side. And so, in this problem, when we wrote the A inverse on the left side of AX, you need to write it on the left side of B. So the second one, right? If I'm going to apply A inverse here, you need to apply A inverse on the right side of B. Notice that in both cases, it's going on the same side of the two expressions. Okay, so now that I've gotten that out of the way, I hope it's important. I hope you recognize, and I know it's important, I hope you recognize that in order to solve this problem, in order to solve either one of these problems, I'm going to need to know what the inverse of A is. So pause the video for a second, stop listening to me for a minute, find out what the inverse of matrix A is. So the first thing you definitely need to do is you need to find the determinant. Right? So first of all, what is the determinant of A? Well, it would be 2 times 4 minus 3 times 3, which is -1. So your inverse should be 1 over -1. And then remember, we switched the positions of A and D, and we changed the sign of B and C. So I've got that. And then I can simplify a little bit further by sort of distributing the -1 into the whole thing. So I'm getting the inverse to be -4, 3, 3, -2. Okay, so now what? Now, I'm going to sort of move this up a little bit, and I'll have to do these problems one at a time. So first we're going to tackle this one, the AX equals B. So AX means 2, 3, 3, 4 times X equals B, which is 5, 0, 1, -3. And the idea is, if I want to get rid of this A matrix, I'm going to take the inverse of A, which we already found out was -4, 3, 3, -2, and I'm going to apply it to the left side of both of these matrices. Okay? Now on the left-hand side, we could multiply these out, but if we did our inverse properly, what should happen here? This thing should be turning into the identity, 1, 0, 0, 1. And why is that? That should be because a matrix times its own inverse will always give you the identity. So the identity times X equals, and this one I'm actually going to have to multiply out. So if I multiply this times this, I end up with -20 plus 3, so that's -17. And when I do first row times second column, I get 0 from those and -9 from those. So that's 0 plus -9. Alright, so I've got -9 here. Continuing on, 15 and -2. So 15 plus negative 2, that's 13. And then the last one, 3, negative 2, and 0, negative 3, is 0 plus 6. Oops. So I'm ending up with 6 for the last one. We're almost done with this. Remember, what happens when you multiply the identity times anything? Remember, the identity times anything is supposed to just be that thing. So x is negative 17, negative 9, 13, 6. That's our answer. Okay? So we solved that matrix equation by using the inverse. Okay? So that was the first half of this question. The second half of this question was that I had asked you to also solve the matrix equation. Let's see here. It was xa equals b. In other words, x times the A matrix, which was 2, 3, 3, 4, equals the B matrix, which was 5, 0, 1. Those are a little bit close together. It's not supposed to be 50. It's supposed to be 5, 0, 1, negative 3. So I really want you guys to pause the video, figure out where you're going to apply the matrix to both of these, apply the inverse, and then do that and work through it. So at the very least, set it up, and then check your setup, and then work it out. So in order to get rid of the A matrix, I need to apply the inverse here. My A inverse was negative 4, 3, 3, negative 2. And so because I applied that on the right side of this one, I applied on the right side of this one. Negative 4, 3, 3, negative 2. So just like last time, I'm going to get x times the identity, 1, 0, 0, 1. On the right side, again, I hope you guys have already multiplied this out, or that you're going to pause it now and work it out on your own. So I'm going to not show the work for this one, just to keep the video a little bit shorter. Multiplying those is going to give me negative 20, and then I'm going to have 15, and then, let's see, negative 4 and negative 9 is negative 13, 3 and 6 is 9. And so just like last time, that identity doesn't, the identity times x is x, so x is this matrix, negative 20, 15, negative 13, and 9. And you'll notice that I got different answers to these two things, and I managed to fit them both on the same screen. When I had ax equals b, it gave me this answer. When I had xa equals b, it gave me this one. It makes sense that I'll have different answers because matrix multiplication is not commutative. You can't do it in whatever order you want. So I really hope you guys caught from this example the idea that the side that you multiply your inverse on matters. I think I've got 2 more examples of this that I hope are examples you guys can do on your own and sort of check and make sure you're getting the idea. Alright, so in this one I added one extra level of complexity I want us to solve this matrix equation. This time, it's some matrix times x plus some other matrix equals some matrix. And I really hope that you guys can see this problem as being the same thing as this. Right? If you had this equation, you would subtract the 2 over, then you would apply the inverse of 3 to both sides, and end up with x being 1. Right, not a big deal. It's the same thing here, but instead of being regular multiplication and addition, it's matrix multiplication and addition. So your first step here should be to subtract this matrix over, then it should be to apply the inverse of this matrix, and then you'll be done. So what I'd recommend you guys do is sort of like do one step at a time. Do the subtraction, and then check your work with me. And then find the inverse and check your work with me. And then finish the problem and check your work with me. Please don't just watch me do this. I want you guys to try and do it on your own. Right? So the first step, as I said, is to subtract this matrix on both sides. Right? Doing that means that the left side is just going to be 3, 2, 6, 1, x equals. Now on the right side, remember with matrix subtraction, you just do piece by piece. So first, 2 minus 1. That gives me 1. Next, negative 4 minus negative 3. Negative 4 minus negative 3, that's going to be a negative 1. It's supposed to be a 1. Then you've got 0 minus 5. That's negative 5. And finally, I guess upside down triangle. Upside down triangle, 3 minus 2 gives me, wow, another 1. It's somewhat less exciting than I wanted, but that's okay. So at this point, hopefully you recognize you've got a problem that's just the same as the previous one, right? I now have some matrix times x equals some other matrix, right? What is the next thing that you need to find in order to solve this problem? I hope that's something that you're thinking about right now. If you need to, pause the video and think about it. You need to find the inverse of one of these matrices. And which one is it? Right? If I want to solve for x, then the matrix that needs to move is this one. So find the inverse of that matrix. Right? You should find that the inverse of that matrix is, first of all, 1 over its determinant, which is 3 minus 12, so negative 9. And then we've got switching these around, changing the signs on these guys. Now this is a perfect example of a case where I could distribute the 1/9 in if I wanted to, but it's kind of a mess, so I don't think I'm going to do it. Right? I also want to show you guys how you can, if you feel comfortable with this, how you can sort of shortcut a little bit of work here. It's not a lot, it's just sort of notation, right? Where am I going to use this inverse? I should be using it on the left side of both of these equations, right? So I don't know that I really need to write it. What happens when you apply that inverse here? Like in the long run, what's going to happen in this problem? What's going to happen is that the inverse will multiply with this guy and effectively cancel out, leaving me with just the identity times x. Now on the other side, I'm going to have to show my work. I'm going to have to write down that first of all, it goes on the left side, negative 1/9, 1, negative 2, negative 6, 3, times my original matrix there, 1, negative 1, negative 5, 1. Okay? So now, on the left side of this thing, I've got just x. On the right side of this thing, like I've said before, you could distribute the 1/9 in, but it's a disaster. I would rather multiply these things first. So again, great opportunity to practice your matrix multiplication. Take a minute and multiply those on your own. You know, leave the negative 1/9 out front, but multiply those things out and see what you get. So hopefully you've already paused and done that. When I do the first row times the first column, I get 1 and 10, so that's 11. Then I'll have first row, second column, that's negative 1 and negative 2, so that makes negative 3. Then the second row and first column, this is negative 6, this is negative 15, so that's negative 21. And finally, second row, second column, this is 6, this is another 3, so I end up with 9 for that one. So then the last step we take is to distribute that 1/9 in. And again, you could leave your answer like that, but I don't know, I mean, it's nice to distribute it in. Negative 11/9. This is 1/3. This one down here would be positive 21 over 9, but that'll reduce to 7/3. And this last one down in the corner is negative 1. I suppose they're all in corners, but, you know, whatever. Alright, so there we go. Yay, we finished that one. I've got one more example for us that I think is going to be quicker, so we'll look at that last one. This example really leads into sort of where I'm going in the next lesson after this one. So this is a simpler problem, one that's going to be a little bit quicker, and it does it does have some neat applications and the stuff that we're going to do soon. So if you're going to solve this thing, again, I hope you recognize that if I want to solve for this x, I need to find the inverse of this matrix. So pause the video, find the inverse of that matrix. So if you want to find the inverse of this guy, we know that first we have to do 1 over the determinant. The determinant will be negative 5 minus negative 8. So that's going to be positive 3. And then we switch the positions of A and D, change the signs of the other two, and this thing is my inverse. Right? Again, I could distribute the 1/3 in. I'm going to skip it here. Next big question. Where is this inverse going to be used? Like specifically, where are you going to put the inverse in this problem? Does it go on the right? Does it go on the left? Like where does this thing go? Because it has to go on the left side of this matrix, it has to go on the left side of this matrix. Okay? When I apply it to this side, what happens? On that side, I end up with the identity matrix times x. On the right side, I'll have 1/3 of my matrix, -1, 2, -4, 5, times my little 2x1 matrix, 7, -3. Left side here, I end up with just x. On the right side, I'm going to leave my 1/3 out, and I'll just do the matrix multiplication. Now, it's interesting to note, this matrix is 2x2, this matrix is 2x1, so because these two numbers here are the same, I can multiply these. What will the dimension of the resulting matrix be? It should be 2x1. In other words, it's going to be another little column matrix. Alright, so this should be real quick. Row times column, that's -7, and another -6, so that's -13. And then second row and column, this is -28, this is -15, so that makes -43. Is that right? 28, 15, yeah, 43. Cool, and so yay, I mean, we're basically done. That means x is, the answer matrix is -13/3, -43/3. And there it is. So, I know this is sort of a long video. This is all about, hey look, we use inverses to get rid of matrices. It's kind of like, again, and I should have said at the beginning of the video, I could see somebody saying at the beginning of this problem, like, oh sure, the way that we solve for x is by dividing by this matrix. There really isn't any such thing as dividing by a matrix. What we do is we multiply by the inverse of that matrix, and I totally should have said that at the beginning of this video. Oops. Whatever, we dealt with it, right? So long story short, we use inverses when we want to solve equations, and we apply the inverse to get rid of the original matrix. Yep, so I'll see you in the next video where we apply this stuff even further.